Good afternoon, everyone. A small turnout for this meeting today, but it's being recorded, so plenty of chance for people to watch it afterwards. Welcome to this online project open house for the Geoscience BC project, Amplification of Seismic Ground Motion Hazard in Fort St. John, Dawson Creek area. My name is Richard Truman. I'm the Vice President of External Relations with Geoscience BC, joining you today from Vancouver in the traditional territories of the Musqueam, the Tsleil-Waututh and the Squamish Nations. The research being presented today pertains to northeastern BC and the territories of the Treaty 8 First Nations, who I know have expressed quite a bit of interest in this research. I'm joined today by the lead researcher on this project, Dr. Pat Monaghan, by Geoscience BC's Manager of Energy and Water, Randy Hughes, and in the background by Geoscience BC Communications and Membership Manager, Virginie Pochard-Linage. Before we get started, just a couple of housekeeping notes. So this meeting is being recorded. We will make the introduction and the presentation available on our YouTube channel in the coming days and up on our website as well, but we won't publish the Q&A session after the presentation. Pat's main presentation will also be available as a PDF on our website after today, and you'll receive an email with links to the video and to the PDF as well. We expect to wrap up around about 6 p.m. Pacific time or 7 p.m. Mountain time. So we should have plenty of time for questions after Pat's presentation. If you do have a question, you can use the raise hand feature in the reactions menu at the bottom of your screen. We'll then ask you to turn on your microphone and your camera, or you can just type a question into the chat and we'll read it out for you. If you are watching the recording, or if you'd like to follow up after the meeting, you can email us and we'll get back to you with answers to your questions. You can email info@geosciencebc.com. That's info@geosciencebc.com. If you are not familiar with Geoscience BC, sorry, excuse me a second. If you're not familiar with Geoscience BC, we generate independent public geoscience research and data about Geoscience BC's minerals, energy, and water resources. This helps to advance knowledge, inform responsible development, encourage investment, and it stimulates innovation. All of our research is public. And earlier this year, we launched Geoscience BC membership. For people that have already joined, thank you. If you haven't done so already, I encourage you to join as a corporate, an individual, a student, or an associate member. Geoscience BC membership makes it easier for a wide range of partners to provide more input on and benefit from Geoscience BC research priorities and project ideas. And it brings together industry, academia, communities, indigenous groups, and governments to achieve shared goals and increase the impact of our research. To join Geoscience BC, you can visit geosciencebc.com, or you can use the QR code that's on the screen right now. So personally, I'm really pleased to be involved in this evening's open house. It doesn't seem very long ago, back in 2019, that we were in a room in Dawson Creek talking about the planning for this project, and we had some great feedback, and that was really helpful, I know, for Pat in working on this project. And here we are with some really important research completed. The report, the data, and the maps are all available for you to look at. I'll put a link to the chat once in the chat. Sorry, once Pat starts talking. And I know Pat has put a lot of work into putting together a detailed presentation this evening. So, Pat, if we have some cooperating technology, over to you to share your screen and start your presentation. You should note, Pat, that I have muted you, so you'll need to unmute yourself as well. There we go. I see you're unmuted, Pat.
Okay, I think I'm unmuted now. Everybody can hear me, I hope.
We can hear you fine. Yeah.
Okay. Well, good evening, everyone. Thank you for joining. Today, I'm going to discuss the results of our project of amplification of seismic ground motions in the Fort St. John and Dawson Creek area. And first of all, I want to acknowledge all my co-authors. Of course, starts off with me, but Brad Hayes and his colleagues at Petrel Robertson, a geological consulting firm in Calgary, Caitlin Googans and Cliff Candy and their colleagues at Frontier Geosciences in North Van, and at Oki, formerly with Northern Geo in Fort St. John. Now, the objectives of this study are to map areas in Fort St. John, Dawson Creek area susceptible to amplification of earthquake ground shaking. And ground shaking, as I think most of you probably know, can vary considerably due to local soil conditions. Sites on soft soil experiencing considerably stronger shaking than bedrock. And here I should emphasize that when I use the term soil, I'm using it in an engineering and seismological sense, which means basically all unconsolidated materials down to bedrock. I know some of you, in particular any people, agriculturalists, will have quite a different definition, but because I'll always slip back to this definition here, I thought I'd better get that definition out front right away. So the focus is on determining areas that may experience stronger shaking when an earthquake occurs, rather than where and when the earthquakes themselves will occur. This area was selected because it's the most populated part of the Montney Play area, and there have been a large number of induced earthquakes in the area. And it's a follow-up to a more general study of the Montney Play that was completed 3 years ago. Now, most events are pretty small. They're from less than 1 to magnitude 4.6. The strongest ground motions are really at the lower bound of published damage thresholds. And so most of these earthquakes are small, but even so, they're still disturbing due to the frequency of occurrence and the noise generated, and of course, the questions that arise in people's minds as a result of that. There's another basic question, and that is, these are small earthquakes. Magnitudes 1 and 2, they're commonly felt in this area. And why is that? Because they're relatively small, or is there something else? And I think I intend to show you that, yes, there is something else. Now, just a brief explanation of the amplification of ground motion. As I mentioned, ground motions are considerably amplified in soft soil. And this is a graphic from the 1989 Loma Prieta earthquake in California, in San Francisco Bay Area. It's a map of Oakland. And you can see on this map in pink, there's a bedrock outcrop. In yellow, this is where sand and gravel is exposed. And in white, these are areas where soft mud is at surface. And these are 3 recordings of the same aftershock at stations on these 3 different geological units. You can see that on the bedrock, the vibration is pretty limited. It increases considerably on sand and gravel, but it really takes off in the soft mud location. And just a comment about earthquake waves. The earthquake waves through the earth are 2 basic types. There's the pressure wave, and that's the direction of vibration is parallel to the direction of the ground motion. And in this case, the ground motion is, or the wave is going this way, and the vibrations are parallel to the direction of propagation of the wave. And it's like a sound wave is actually an example of a pressure wave in air. And visually, it's like a pulse in a slinky. And you can see that there's a compression here and dilation here. The other type is the S wave or shear wave, where the vibration direction is actually perpendicular to the direction of the wave. Wave is going this way, and the vibration is going this way. It's analogous to an ocean wave. Although, of course, ocean waves bottom out. And the important takeaway here is that P waves are faster, but it's shear waves that cause the most shaking. And as shear waves slow down as they approach the surface, the amplitude, that is the magnitude of the vibration, increases, causing amplification. And this is analogous to how ocean waves, as they slow down approaching the shore. And amplification, so it's controlled by the shear wave velocity of the soil and the shallow bedrock. And this picture here shows us collecting shear wave velocity in a borehole in the ground bridge area. Now, there are 2 types of amplification that are important and that we're looking at in this study. I have to recognize that earthquake ground motions are a mix of a wide range of frequencies or periods of vibration. And I'm going to use frequencies and periods. They're essentially the same thing. Frequency is the inverse of periods. And that's frequency is the number of cycles or pulses per second. And periods are the number of the seconds that would take in a particular pulse. So if you know one, you know the other. I prefer to stay using the word period because that relates better to geological thicknesses and also the stories of the buildings. But like I said, there are a mixture of wide range of frequencies. And it's just like our voices have a mix of, the sound of our voices has a mix of frequencies. So that's what gives it its richness and its distinctiveness. Now back to the two wave types of amplification. One is called broadband, and that's the ocean wave analogy. And the amplification occurs over a broad range of periods. So basically, most of what the earthquake throws at it can get amplified under those circumstances. The other important aspect is resonance. And that's amplification of a specific period of ground motion that's equivalent to the site period. And the site period is the natural period of vibration of the site. And I'll get into that a little bit further down. And just think about the earthquake waves, in fact, reverberate between the surface and the bedrock soil contact, or another geological contact. And the site period or frequency is a period of vibration at which the upgoing reflective waves reinforce each other, thereby amplifying that particular frequency or period. And the example we've all seen in cartoons is the opera singer shattering a wine glass, singing at the same pitch as the glass pings. Site period is directly related to soil thickness and is also controlled by the shear wave velocity. It increases with the thickness of the soil column. The amplification magnitude itself is due to the velocity and density contrast of the soil, bedrock, or another geological contact. And buildings with the same period as the site period are particularly affected. And a good rule of thumb is that building's period would be about 0.1 second per story. And the important takeaway is that resonant amplification can produce ground motions that are the strongest in an area. We're demonstrating that as we go down. Now, ground motion amplification is commonly estimated by the time average shear wave velocity in the upper 30 meters, and we call that the VS30. And this is commonly used in building codes, like our own National Building Code. And based on various VS30 ranges, and these are the numbers right here, in meters per second, 5 site classes have been defined, going from A to E. And as you go down through the alphabet, you get into lower VS30s and greater amplifications. And what this column shows is the amount of amplification relative to site class B in the other site classes. And what this is stating here is that here on site class C, for the peak ground velocity, that's a PGV, on site class C, the PGV would be 1.5 times greater than it would be on a nearby site on site class B. And on site class D, the factor is 2.2 times greater than on site class B. Now, this is good for broadband amplification. Doesn't really deal with resonant amplification that well, as I'll demonstrate. So the tasks of the project, first of all, to revise the superficial geological mapping, then also preparation of a geological map representative of the shallow subsurface geology. We're interested in what's below the surface, not just what's at the surface. We conducted a 2-week field program. We interviewed residents regarding their experiences. We acquired new shear wave velocity data. We compared the geological data we had with recently recorded earthquake data to see whether our models work. And we investigated the susceptibility to resonance, putting it all together to map the susceptibility to ground motion. And I'm also going to comment briefly on the earthquake noise and drilling vibration reports that we were described to us. Now, in the revised superficial geological mapping, I have to recognize that the initial maps were made by very good geologists, but because so many of the geological units have rather distinct topographic expression, and that we have available to us so much better topographic data now than they did, we're able to really considerably improve on the mapping that they did. And so we did just that. And what I want to focus on here is on some three principal environments that I'll be focusing on. One, and in these areas in bright green and kind of softer green here, these are upland areas where the original geologist map is described as having thin deposits of till over bedrock. And just driving through these areas and looking at the topographic maps, so the expression is quite different. These are high relief uplands with fairly thin soil, bedrock, fairly thin soils over bedrock. In the lower relief uplands, more gentle topography, much more suitable to agriculture. The bedrock is a little bit deeper, and the behavior under earthquake loading is quite different than it is here, that I'll show. Another principal environment is there are these glacial-lacustrine plains and benches. These are joined in major rivers like the Peace and the Pine, along the Kiskatnaw, and also form the valley bottom and a number of the smaller drainages. And when I say glacial-lacustrine, these are mantled by silts and clays that were deposited in glacial lakes at the close of the last glaciation. Now, like I said, we're interested in the subsurface, not just the surface. And the surface is important, but you've got to understand the subsurface too. So we assembled a database of boreholes, and this gives all the numbers of the different types. This map shows the distribution. So a fairly good distribution, although this is a big area. So, I mean, we did have a lot of borehole data. Important point is that these borehole types, the oil industry gamma ray logs and water well logs, these are all in the public domain. And tables listing these and describing these are included in the report. Now, we collect a lot of the geotechnical borehole data, and these are proprietary. Nobody has to provide this to us. And we obtained these from what I described as the usual suspects, public agencies such as BC Highways, BC Hydro, the cities, school boards, Northern Lights College, etc. But we also were able to get the data from all of the principal oil and gas operators from their gas plants and similar facilities. And this is a map that we were able to create from that. And you can see in the high relief uplands and the low relief uplands, soil thicknesses are generally less than 15 meters. But in the glacial-lacustrine plains, you get much thicker deposits of sediment over bedrock, commonly exceeding 100 meters. So as I mentioned, understanding the shear wave velocities of these deposits is very important. So we had to improve on the shear wave velocity database that we had. And shear wave velocity is shortened to be VS. We obtained shear wave velocity at 28 new sites during the course of this project. We had some data at 14 sites from a previous study. And we were able to obtain proprietary VS data at a number of sites as well. So we had a reasonably good database. And what this slide shows is plotting the depth of bedrock versus the VS30, that is the shear wave velocity in the upper 30 meters. On the left-hand side, you can see on this axis, you've got the depth of bedrock. This is on a log scale, so this is 1 meter, 10, 100 meters. On this axis, you have the VS30, but I've got the site classes reported at the top. And you can see by this, there's a reasonably good plot through here. And the site class CD boundary occurs at roughly 15 meters. There are some exceptions. There are some site class C sites which have greater depths of bedrock. And there are some site class D sites that have far less than 15 meters. In fact, down here, these 3 points represent probably another trend. And these represent points in the low relief uplands where the upper part of bedrock has been extensively weathered and behaves more like soil than it does like bedrock. The BC boundary is at approximately 3 to 5 meters, depending on how you plot this. I've plotted this a couple of different ways. That's why I have a range of values here. Now, we also compared the recorded ground motions with the geological data. And this is from an earthquake data set that was compiled by Ali Mahani, my friend and colleague. And we have over almost 1,300 records of 300 events. And this slide shows the distribution of the seismograph stations where these data were recorded. And in these comparisons, we compared the actual recorded ground motions with those predicted by 2 ground motion prediction equations. And what these ground motion equations do is they predict the ground motions at a site based on the magnitude of the event and distance from the source. And this is usually with respect to some reference condition, and it's usually site class B. And the difference between the recorded and the predicted, that's the first order estimate of amplification. Now, I've used 2 different equations. Each uses slightly different subsets of the data. They each have their strengths and weaknesses. And the details are presented below that you can peruse later at your leisure. And what I'm showing here is the average PGA, that's peak ground acceleration, and PGV amplifications, and PGV is peak ground velocity by a geological setting. And we compared the averages 2 ways, one using all the data, another using station averages by station. And quickly determined that in the high relief uplands, these are the areas with the thinnest soils, there we saw the lowest average ground motions. So what on these tables, I'm showing the relative amplification, or how much greater the average ground motions are in the low relief uplands to the high relief uplands, and similar but to the glacier lacustrine to the high relief uplands. Now, when you do the comparisons by the number of records, the PGA and PGV amplifications are relative to high relief uplands are less in the low relief uplands than in the glacial lacustrine. And this, when we look at the number of stations, this relationship is reversed. So what can we say by this? Well, I think we can still say that the high relief uplands have the lowest average ground motions, but in the low relief uplands and the glacial lacustrine settings, it's probably relatively similar. There seems to be some depth of bedrock control here, but not completely, because the depth of bedrock is considerably different in these settings, this setting, than in these, much deeper in these settings. So this is doing the same kind of comparison by calculating the average amplifications by depth of bedrock range. And the lowest ground motions, again, on average, are in the thinnest depth of bedrock range, which we use 0 to 7.5 meters. And we're assuming this to be around site class B or close to it. This table shows the relative amplification relative to the thinnest depth range compared by the 2 different ground motion equations. And as you can see in these, using this equation here, in the 7.5 to 15 meter range, which we've shown, I think, this is generally in site class C. The amplifications are for PGA about 1.4, PGV 1.9. And greater than 15 meters, they're greater still, 1.6, 1.7 approximately, and 2.3. And these amplification factors are roughly they're consistent with what you would find with published amplification factors for these site classes. But this doesn't hold up when I use the other ground motion equation. That in that case, the amplifications are greater in site class C than they are in site class D. And that's not what you would expect from the site class model. But this certainly suggests, now this is partly because different earthquakes are incorporated into this equation because these are the ones more suitable to be included, analyzed by that model. But it also suggests that resonance is playing a significant role here. We've got thinner soils. They should have less amplification, but in fact, they have greater. And talking to residents, they commonly experience greater effects of these earthquakes in thinner soils than in upland settings. So again, there's a lot of evidence for resonance. And I've looked at it through a number of different ways, but I just want to show an example of how this manifests itself. This slide shows two representative shear-wave velocity traces this is from surface geophysical testing at two sites, one at a valley bottom site and the other at a hilltop site. These are 1.5 kilometers apart at the west end of Parkland Road. And on these plots, this is the depth axis here. You can see it goes from 0 meters, 10, 20, 30. Same scale over here. On this axis, you've got the shear-wave velocity going from 0 to 1,000 meters per second. Similarly over here, 0 to 1,000 meters per second. This site here in the valley bottom is site class D. This site here, it's site class C. And yet the residents report stronger ground motions in this setting than here. Now look at these plots here, and here. In this plot, there's a sharp velocity contrast with a low velocity layer with a sharp change at 5 meters. We can compute the resonant period or frequency, and here it's at about 0.11 seconds. And this is within the period range of the dominant ground motions, which are 0.1 to 0.3 seconds. At the valley bottom site, we've got similar low velocity layer. It's much thicker. The velocity contrast is at 15 meters. Here, the resonant period is 0.32 seconds. It's longer than the period of the dominant ground motions. And this is an example of how the resonance susceptibility is greater at thin soil sites in the opposite settings. So mapping, putting it all together, where depth of bedrock is less than 15 meters in the high relief uplands, we're interpreting these to be primarily site classes B and C. It's got the lowest recorded ground motions, and that is the lowest amplification. Outcrops are common in this area. So depth of bedrock is commonly less than 5 meters if you see in boreholes. So we see site class B as common. What we're saying in here, when the soil is thin, it's very thin. So we say these areas are susceptible to very low to low broadband amplification and low to moderate resonant amplification. In other settings, these are generally in site class C with less than 15 meters of soil, and locally in D, outcrops are uncommon. Depth of bedrock is much more variable. That, in this area, you can have much greater range of thicknesses down to of soil. Site class B is uncommon, but weathered bedrock is common. And the depth of bedrock range of 5 to 15 meters is also common. And with large velocity density contrasts in the period range of the dominant ground motions, this makes this area susceptible to particularly susceptible to resonance. So what we summarize this as saying is susceptible to low broadband amplification and moderate to high resonance amplification. The strongest ground motions may occur in this setting. In the depth of bedrock, 15 to 30 meters, there's amazing site class C, a bit in site class, or amazing site class D, I'm sorry, some in site class C. And where it's in greater than 30 meters, it's pretty much all in site class D and susceptible to broadband, moderate broadband amplification, but resonance is probably going to be pretty low. This depth range is sort of intermediate between that and that. And when we show this on the map, you can see in the high relief uplands here, these have susceptible to low amplification. In the low relief uplands, in the thin soils, we're using this is the depth of bedrock map. We're just using this as a first order control over amplification. But in the low relief uplands, you've got susceptibility. Broadband amplification isn't going to be an issue here generally, but certainly resonance amplification will be. The 15 to 30 meter depth range is not well represented here, but when you get into the greater than 30 meter depth of bedrock range, particularly in these glacial custom plains, these are going to be susceptible to broadband amplification. That's the ocean wave model, but resonance, not so much. That's the opera singer model. I want to talk a little bit about earthquake sounds. These are the sounds due to the earthquake itself, and distinct from the shaking of buildings or contents. And they're caused because the P waves of the earthquake, these generate sound waves. And because they precede the S waves that cause the shaking, you hear the sound first. It's like you can hear it coming. A lot of people have expressed it exactly that way, and I've experienced it myself. And these are commonly associated with low magnitude earthquakes. And for very low magnitude earthquakes, and 1 and 2, sound may be the only effects observed by people. It's my contention that these are more likely to be heard where bedrock is shallow. That is hilltop sites, upland sites, rather than valley bottoms. And examples in Victoria and Italy. And the reason for this is that these sounds are the low end of the frequency range audible to humans. And the thicker soils in the valleys can filter out the higher frequencies. So basically, if the higher frequencies are filtered out, there's nothing audible left. Furthermore, they're commonly reported by residents, particularly on upland settings in the study area. These upland settings are more susceptible to resonance amplification, particularly the low relief uplands. And I think it's an important contributor to the disturbance of resonance. And I think we need to know more about residents' experience of the earthquake sounds. It's not something I really focused on, but I think it's something that I couldn't ignore completely. Another thing that was kind of commented on by people that I didn't really pursue extensively is during vibration. It was reported by several residents in Briar Ridge. Either they could feel the vibration or hear a very high-pitched sound from that. Barely audible, but distinct. It's rarely commented on elsewhere. And is this an example of topographic amplification? Because Briar Ridge is a very distinct, narrow, steep ridge. Or is it because elsewhere where earthquakes are being felt, that's what people are more concerned with? I don't know the answers to those questions, but I think it's something worth pursuing. So my conclusions: amplification is widespread. It's occurring in a lot of different settings. It's both broadband and resonance, but it is different, and of course both types can occur. But it may explain in part why small events are so widely felt in this area. You've got a lot of areas which are susceptible to amplification. Depth of bedrock is a first order geological control over amplification. Where depth of bedrock is less than 15 meters in the high relief uplands, site classes B and C, susceptible to low broadband, that is the ocean wave model, and low to moderate resonance, so that's the opera singer. High probability of earthquake sounds. Where depth of bedrock is less than 15 meters in the other settings. It's generally in site class C, locally in D. susceptible to low broadband amplification, but moderate to high resonance. So in this area, the opera singer really is the strongest. And the strongest ground motions may occur here. And these are in the approximate period range of a 1 to 3 story building. So that can affect a lot of people. There's also higher probability of earthquake sounds. And I think it's an important combination for this area. Where depth of bedrock is greater than 15 meters, it's usually site class D. It's susceptible to moderate broadband amplification, but low to moderate resonance. So here, the ocean wave model is more significant. And there's a lower probability of earthquake sounds. It's important to recognize these are qualifications of this maps of the study. They're intended for regional or preliminary assessments. They do not address the seismic hazard directly because the regional variation in seismicity is not included in these maps. They don't represent seismic risk because the type and quality of construction is also very important. Other types of amplification are not considered, and other potential seismic hazards are not considered either. They're based on interpretations of geological data. The boundaries of these geological units and contours are approximate and will change as more data become available. And they do not address man-made alterations to the ground conditions, nor do they consider the seismic stability of dams. This lists all my people who assisted us in this project, a vast number. These projects don't come along without a lot of effort and a lot of assistance from other people. And finally, I want to thank you for your attention and sort of open this up to any questions.